Back when the internal combustion engine was first used on wheels, no one gave much thought to its carbon footprint. Kind of how we got to the point we're at today. Nearly a quarter of carbon emissions come from the transportation sector. For manufacturers under pressure now from consumers and governments, electric vehicles are seen as the new direction. Batteries not just at the center of the cars, but central to their green success. So, are they greener? How much so? Lithium is the component of choice for today's batteries, capable of packing more than 10 times the power of a daily household's electric needs into a car. And that's led to big lithium demand, expected to at least triple by 2025. Already, mining is eating up freshwater supply in South America's lithium-rich regions, requires harsh chemicals in extraction in North America. Then there's copper, nickel, cobalt, all with dark sides of their own.
We are Group 11 and welcome to our presentation. As the video prior to this outlined, current transportation methods are heavily reliant on the use of fossil fuels to both use and manufacture vehicles within the transportation sector. In the United States, the transportation sector accounts for almost 25% of all CO2 emissions. The aim of this presentation is to investigate and introduce sustainable hydrogen generation techniques which could feasibly be integrated into modern infrastructure. My name is Ali Al-Bablawi and I am the Senior Design Engineer.
My name is Lorenzo DeFinis and I am the Chief Engineering Officer.
I'm Kyle Alden and I'm the Chief Technical Officer.
Matthew Travers, Chief Financial Officer.
An increasingly important issue that our civilization is responsible for is the demand to reduce carbon dioxide emissions to collectively prevent global warming. In the United States alone, the transportation industry accounts for 28% of all CO2 emissions. Popular industries are emerging to offer solutions in the effort to reduce CO2 emissions, such as the market for electric vehicles, which has been rising by 40% year on year. EVs seemingly offer many benefits which increase the environmental sustainability. The primary advantage that EVs offer over traditional vehicles is that they produce no harmful emissions. A disadvantage to EVs, which is often overlooked, is the manufacturing process related to EV have been found to produce greater emissions than their gasoline counterparts. A popular alternative which potentially offers greater environmental sustainability while negating many of the limitations which are associated with EVs are hydrogen-fueled cars. The current problem associated with the widespread adaptation of hydrogen-fueled vehicles is the sustainability of current hydrogen generation and extraction techniques. Currently, 95% of hydrogen in the US is produced through methane reforming, which is detrimental to the environment and negates the increased sustainability which hydrogen offers. The objective of this project is to work to offer solutions to reduce the CO2 emissions stemming from the transportation sector. After a thorough analysis of current transportation modes, it is apparent that promoting the shift towards utilizing hydrogen as fuel offers the greatest solution to reducing CO2 emissions. Currently, the production of hydrogen is accomplished through manufacturing processes that are detrimental to the environment and thus negate the many benefits which accompany the utilization of hydrogen as fuel. The scope of this project is to identify and analyze sustainable hydrogen generation techniques which offer the potential for wide-scale implementation within the USA. The design constraints which govern our proposed design can be seen on screen now. These constraints were chosen to ensure the design promotes the use of hydrogen as fuel and sustainable from generation all the way to end product. The constraints were also chosen to allow for the design to be easily expandable and implementable into modern-day infrastructure. The criteria presented in this section provide the foundation for the basis of each of the designs, as well as the goals and desired outcomes which each of the presented designs aims to accomplish. To incentivize the move towards hydrogen generation, the promotion of low production costs will be essential in swaying consumers and manufacturers. The system must also be as efficient as it is cost-effective to further promote the widespread adaptation of hydrogen. Safety is at the utmost of our concerns, and maximizing the safety of the design was an essential benchmark which we aim to meet. Finally, maximizing the sustainability and performance of the designs were criteria which we thought were essential in determining whether or not the selected design will be successful in implementation or not.
The three iterative designs that were analyzed include an SOEC system, a biomass gasification chamber, and a PEC system. The SOEC consists of an anode, a cathode, and an electrolyte. Water at the cathode combines the electrons within the system from the DC power supply in order to form hydrogen gas and oxygen ions. Biomass gasification is a hydrogen production method that utilizes a combination of steam, heat, and oxygen in order to convert existing biomass into hydrogen gas. Within a PEC system, hydrogen is produced using sunlight. Electrical energy is created using semiconductor materials and is comparable to those seen within other various photovoltaic cells. The electrical energy created using sunlight spurs the splitting of water into hydrogen and oxygen gas byproduct. 3 sensitivity analyses were performed on the 3 hydrogen production methods. The table on the top left placed an increased weighting on cost-related factors. The table on the top right, an increased weighting on accessibility and longevity, and the bottommost table on renewability and efficiency. The design criteria were developed based upon the following parameters. The cost to installation section was developed based upon a benchmark from the U.S. Department of Energy. The safety and accessibility section was largely subjective and depended on the functionality of current designs. The renewability and sustainability section was determined by the overall global warming potential of each hydrogen production method. The efficiency and lifetime/maintenance sections were benchmarked off the overall functionality of a steam refor plant, being that it is the most efficient method of hydrogen production that currently exists. As you can see within each table, the PEC water splitting system scored the highest within each sensitivity analysis, and thus was chosen as our final design.
The proposed PEC system consists of 4 main components which have all been designed to be scalable for larger or smaller projects. First, this particular design is built under the assumption that a maximum of 64 customers will be serviced in a single day. This assumption governs the overall requirements of each component in the system. For example, this system needs a total of 32 PEC hydrogen production units, 15 solar panels, 3 hydrogen storage tanks, as well as a single centrifugal compressor capable of producing 1.5 horsepower. The individual PEC unit is designed inside of a case made from structural acrylic glass, enhancing the durability and maintaining adequate solar energy transfer. The case features a removable panel for easy access to components that need replacement and maintenance. The unit is maintained at a low pressure of 20 psi at both the water inlets as well as the oxygen and hydrogen outlets. The system converts water into hydrogen using an array of 120 cadmium selenide photoanodes and 120 bismuth vanadate cathodes separated by a Nafion membrane. This allows for isolation of oxygen and hydrogen production, avoiding any post-reaction processing. A centrifugal compressor was chosen to be implemented in this system as opposed to a reciprocating or rotary compressor due to the overall durability and reliability of the design, resulting in less overall maintenance. A 1.5 horsepower compressor was selected based on calculations assuming an adiabatic efficiency of 85%, a water inlet flow rate of 0.116 grams per second, as well as a maximum outlet pressure of 7,500 psi or 50 megapascals. The pressure vessels are designed to provide adequate storage for hydrogen in a gaseous form while avoiding the complexities of maintaining cryogenic temperatures needed for storing hydrogen as a liquid. The tank consists of a cylindrical body and ellipsoidal end caps to maximize structural rigidity and volume. The tanks will be made from grade E fiberglass saturated in a polyester resin due to the high strength properties and relatively low cost. The resulting design is capable of storing 115 kilograms of hydrogen at a pressure of 7,250 psi across a volume of 3.64 cubic meters. The solar panels used are calculated to possess an incidence of approximately 94.28 watts per square meter. This can be used to determine the coverage needed to supply the necessary 1,012 watts to the hydrogen compressor. The proposed design will need a minimum of 10.734 square meters of coverage, which will result in a total of 15 solar panel units.
The total cost of our design is $129,063. This cost consists of various subtotals for the solar panels, electrical components which include instrument wiring, power wiring, and conduit, a total of 3,840 anodes and cathodes, which yield an area of 12.065 meters squared and 3.525 meters squared in total respectively, water piping and high-pressure gas piping, a 1.5 horsepower centrifugal compressor, hydrogen storage consisting of fiberglass and fiberglass resin, as well as the glass components of our design.
A single photoelectrochemical cell is capable of producing 160 kilograms of hydrogen within an average 12-hour day. The calculation can be found on the screen where the amount of hydrogen produced is multiplied by 32 PEC units, which provides the 160 kilograms of hydrogen. Based on the average hydrogen-powered car, which requires 5 kilograms of hydrogen for a full tank, our design can refuel 32 cars in a single day, and when starting the day at maximum storage capacity, it can fuel 64 cars. The successfulness of the device is deemed attainable due to the efficiency from the highly innovative coating applied to the anode, which accomplishes the solar to electrical energy conversion that drives the photoelectrochemical water splitting. Photoactive materials used to coat the anode is a crucial enhancement factor that determines the high yield of the reaction based on its solar to chemical efficiency. A difficult limitation for PECs has been this factor owing to limited light gathering, energy loss related to rapid recombination of photo-induced whole electron pairs, as well as electrode degradation. Various kinds of semiconductor materials have been researched, which has led to the development of hybridization of these oxides with noble metals to enhance the PEC performance. The limiting factor for typical metal oxides were that they require ultraviolet light. However, almost half of the solar energy on Earth's surface is within the visible light region. Although these calculations are complex, a similar study found that the maximum solar efficiency of commonly used metal oxide material could only achieve 2% efficiency if all the UV light were exploited. The United States Department of Energy states a PEC system should meet a conversion efficiency of 10%. This led to the development of cadmium selenide, which is most effective when applied to the anode through spin coating. It can harness the visible light region, which results in an efficiency as high as 32%. This research is essential to the development of this design, which wasn't thought to be feasible until now and can surpass traditional hydrogen extraction methods. Since the PEC system relies heavily on a large water supply and solar energy to drive the reaction, the system can be considered to be environmentally friendly. The source of water is considered renewable, which is defined by the Energy Information Administration as a fuel that can be easily made or renewed. As water is a readily available resource and continuously moves throughout our planet through the hydrological cycle, this allows water to be considered renewable since its reservoirs will always be replenished. The calculation on the screen reveals the mass flow rate of water required to produce the desired hydrogen production, which is attainable from the nature of this renewable source. Solar energy is also a practically inexhaustible resource, making it a renewable energy that won't be in short supply within many generations of human life. Both of these characteristics promote green energy and can greatly reduce the impact of fossil fuels to enable transportation of light-duty vehicles.
All engineering systems should have a large focus on the health and safety implications of their design. The PEC system features a variety of safety measures throughout the design. First, pressure relief valves are installed on each pressure vessel set to maintain a maximum pressure of 7,250 psi to avoid overfilling. Similarly, the low-pressure plumbing features a second array of pressure relief valves that will release oxygen gas into the atmosphere when the internal pressure exceeds 20 psi. The water inlet pipe features a shutoff valve that can control the flow rate of the water and thus limit the chemical reaction process. Next, the design of the storage vessels maintain a minimum wall thickness of 3.2 centimeters, resulting in a factor of safety exceeding 3.5. Secondly, the composite material of the pressure vessel is designed to release hydrogen gas in a controlled manner in the event of a puncture. This means that any explosion risks are extremely low. Lastly, a unique feature of a PEC system is that the byproducts produced only consist of oxygen and hydrogen gas. This eliminates the risk of toxic inhalation that may be associated with alternative hydrogen extraction solutions.
A recent study by McKinsey & Company anticipates that the hydrogen economy could generate more than $140 billion by 2040 and result in the creation of 700,000 new jobs. The state of California is the main area in the United States supporting hydrogen initiatives and has provided $20 million per year over the course of the last decade for hydrogen generation research, and is projected to provide $230 million in funding for these projects by the end of 2023. A total of 7,500 hydrogen vehicles are currently on the road within the state, and projections indicate that up to 50,000 hydrogen vehicles could be on the road by mid-decade. As such, we believe that our design is well stationed to benefit from the many economic and political initiatives supporting hydrogen generation within the state. The cost of one of our PEC systems is low enough to be incorporated within future infrastructure and will be able to assist with fueling the 50,000 anticipated hydrogen vehicles on the road by the end of 2030.
In conclusion, our photoelectrochemical water splitter offers a feasible solution for hydrogen generation and intertwinement with future infrastructure. Thank you for listening to our presentation and have a good day.